Good evening. Sorry, I was muted. Um, Welcome to this fourth session by NPTEL Gate Physics. My name is Amit. We'll wait for 2 or 3 more minutes and then we'll start. So you guys have seen that today's opamp topic, right? You were aware of that as per the calendar.
Yes, sir.
Okay, good. So uh, I'll start with the basic of operational amplifiers, and the negative and positive feedback. What do we mean by inverting and non-inverting? And then we'll start with some problems. This opamp, the questions were, I think there were 13 questions in the last 10 years. So what I'm going to do is I've broken up into 3 weeks. This week we'll be doing very basic questions. Next week we'll be doing I would say an intermediary level questions, but those are circuits which you have seen. These are RC which have capacitance in them. And last week we'll do slightly advanced questions where we'll try to see what real op amps look like. So but we'll be starting slow. That's the idea. And secondly, after op amps are done, what I'll be doing is I'll be doing logic circuits, logic gates, and those ADC, DAC converters, counters, and that kind of stuff. That I think should again take 3 odd weeks, because I don't want to hurry that we solve 10 questions in 1 hour. I'll do 4 or 5 questions which are related to each other, and gradually we'll increase the level of complexity. So that's the idea. After that, we'll do diodes and metal semiconductor junctions. That will take, I think, 2 classes, and final 2 sessions will be on BJT and FETs. So BJT, FET, and diode, usually one question comes every year. Op amp, you get definite at least one question. Some year you get 2 questions. And logic gates, again at least one question. And there are years where there have been 2 questions. Again, these are very I will start with basics, but these are very conceptually simple, and numerically the problems are easy to solve. There's no, like, you have to remember some formula. These are very simple. KCL and KVL, for op amp I'm talking about, very simple. Not even KCL, just the KVL we need to apply, and that's it. We'll see when we solve the problems. I'll start with theory in a couple of minutes. At around 7:05 I'll start, because people are still joining. So I'm audible, right? My voice is not feeble.
Yes, sir. You are audible.
Loud enough?
Yes, sir.
Okay, good. Last session, if any of you people attended, was my voice feeble? Was the audio volume low? That was the case.
No, sir.
Okay, okay, fine. Because I also record my sessions, and in that it was what I saw was that my volume was quite low. So I was worried whether you guys were able to hear my voice or not. Okay, it's all good. Okay, I'll be starting now, and I'll be sharing my screen. You should be able to see the screen.
Yes, sir.
Okay, so this is week 4 gate physics session. My name is Amit. We'll be talking video solutions hosted by NPTEL. Right, what is an operational amplifier? Now, as always, I'll do less talking in this part, you will do more talking. What is an operational amplifier? Can somebody tell me, please?
It performs mathematical operations like multiplication, division, addition, integration.
Okay, that's what you meant to say.
Yes.
Okay, so operational, yeah, and
It is amplifier, so it is also used to amplify signals.
you meant to say this.
Yes.
Okay, so this is what it's supposed to do, right? It's an operational amplifier, so it will perform some operation. These are very, the 4 examples which I have given here will solve these questions, and these are very simple numericals, but it performs operations. Second, it amplifies. Usually it can amplify. Amplifier is a generic term which means it amplifies something, it increases its amplitude. So in this case we'll be restricting to amplifying the voltage. We'll talk about only voltage here. Right, now we know our aim. We must perform some operations and amplify. Now next thing is, how do we do this? We do it this way. So operational amplifier is nothing but a subclass of differential amplifier. Now differential amplifier, what do you mean by that? So this is a typical circuit of differential amplifier on your screen, left side. A differential amplifier will have 2 inputs. So this is your first input, as you can see here. Hold on a second, my pen is not working. Okay, just excuse me, just my pen has stopped working, so just excuse me for a minute, sorry. I'll again share my slides. There is some problem with the software, I need to fix it. Is my screen visible?
Yes, sir.
Okay. The pen is working now. Okay, so differential amplifier has 2 inputs. We call this input as V in plus and this is V in minus. So what the differential amplifier it does effectively is that it takes the difference of these 2 inputs and it amplifies it by a factor. So the formula is written here. So what we have is, we have V out, which is the output voltage, which is measured here. You don't have to just if you don't have to go in depth of this circuit, this is just at device level what an operational amplifier looks like. So if you open it up, it will look something, a differential amplifier looks something like this. So it has a differential gain which denoted as AD times the difference in input voltages. So difference in input voltages would be V in plus minus V in minus. Plus a differential amplifier also has a common mode gain. This means it will V in plus V in minus over 2. This is a standard expression you will find in your textbooks. Now this is a differential amplifier. So how do we convert this differential amplifier into an operational amplifier? If a differential amplifier satisfies these 3 conditions, that AD is greater than AC, means your differential gain is very high, so we can ignore the common term, common mode. This is called common mode gain, so we ignore AC. So we'll say that if it says AD is greater than AC, we say this term goes to 0. Okay, and some other things like low output impedance and high input impedance, you get an operational amplifier. This is what is inside of an operational amplifier, and this is the diagram which you are familiar with. So an operational amplifier has this node is called non-inverting node. Non-inverting. This terminal is called inverting. Can somebody tell me why are they called inverting and non-inverting? Anybody? Am I audible?
Invert the signal by phase of pi.
Correct. By inverting means if I give it a signal, let's say plus 1 volts here, and let's assume this is grounded, so output would be AD times 1 volts with a negative. So let's say the value of AD is 100, so the output voltage would be then minus 100 volts. So this is what is meant by inverting. So whatever, if any signal is provided here, output you will see its inversion. Non-inverting means whatever value you provide, it will reflect here, obviously amplified. That depends on what the circuit inside an operational amplifier looks like, right? And these are 2 other nodes, Vs plus and Vs minus. See, We'll see what do mean what these terms mean in the next slide. Right. So this is, I told you, there is circuitry inside this operational amplifier, and we can model this amplifier using this. So what it is, this is an input V plus, the non-inverting input. This is against second input, this is called inverting input, denoted as V minus. This is our output V out, and these are our see, operational amplifier must be provided some voltages to run, which we can see here. You see VCC and VEE, these are power lines. So in order for current to flow, there has to be some external power that we need to provide, which is being denoted here by Vs plus and Vs minus. So this is, let's, for example, if Vs plus usually can be, let's say, plus 15 volts, then typically Vs minus will be minus 15 volts. S here stands for saturation. We'll just talk about it. Right. And it has an input impedance, this circuit, which we call it as Rn, input impedance. Similarly, this circuit is an output resistance, which we call R out, and this is a dependent voltage source given as G times Vin, where G is the gain. Right. So here are some of the parameters which you will encounter in textbooks and in numerical problems which you are going to solve. Here is the parameter name, the variable which usually is denoted with the ideal value and the real value. This is a very standard thing, and it's very easy to understand. What's an open loop gain? The open loop gain is simply G, like V out. So G would be V out, which I denoted as AD or G or A open loop. OL stands for open loop. This is divided by V out divided by V in plus minus V in minus. This is the gain. Ideally, for an ideal op amp, this is infinity. However, for more real circuits, this is about 10 to the 5. 10 to the power 5 would be 1 lakh. Okay. Second thing is output voltage, denoted as V out. Ideal value is infinite. This means ideally you can get infinite voltage out of as an output in an op amp. This is a fancy scenario. This is not realistic. We do get maximum of VSAT. Now this is important. You cannot go above VSAT. So this will, whatever output voltage will saturate at, let's say if VSAT is plus 15, so it will saturate plus 15 or minus 15. It cannot go beyond that. This is very important. We'll see, and we'll see this in some problems how it's used. Right. Input impedance means if we supply a voltage, how much current will go inside this amplifier. This is what is denoted by input impedance. Ideally, okay, sorry, this is a bit wrong. So this is infinity actually. Rn is infinity, and real value in the real circuits you get some mega ohms, and output impedance is 0. In real life you get a few ohms, like 2 ohms, 4 ohms or 5 ohms, or the order of ohms. So this was wrong. This is mega ohms, this is again infinity, and this is 0. So if input impedance is infinity, means there will be no current. So let's say V plus minus V minus is 1 volts, and let's say Rn is, let's say, 10 mega ohms. So the current would be like 100 nanoamps, which is negligible. So that's what I said. Ideal value is infinity. However, the real value in some real circuits we get some mega ohms. Similarly, output impedance, this value, output impedance, which you see here, ideally it's 0. However, in real circuits it's a few ohms, 2 ohms, 5 ohms, 10 ohms, depending on the circuit and the components, like what BJTs or MOSFETs we have used inside. Right. This is a term which we again see, offset voltage. See, this is due to the manufacturing. In an ideal circuit there are no manufacturing defects, so you get offset voltage equal to 0. However, there is some offset voltage, usually of the order of milliamps, maybe 10 millivolts, 5 millivolts, or 1 millivolts. That's depending. I've just stated the order, that it's around 1 millivolts. Right. Now these are important things. Bandwidth. So under which frequencies? So what is a bandwidth? Bandwidth means, so let's say this is gain versus frequency. We'll visit these terms later, don't worry. This term and this term will I'll spend one whole class on this bandwidth. So it looks something like this. So let's say bandwidth is typically when the gain is high. The range of frequencies when the gain is high. So high means that depends on you. It can be 20 dB, it can be 40 dB, that depends on the application. So the range of frequencies during which gain is high, is that range of frequency is called bandwidth. Ideally it's infinity. Real value, if it's a low pass filter, it will be lower. If it's a high pass filter or a band pass filter, depending on what kind of filter this operational amplifier is behaving as, real value will change accordingly. Hence I'll leave this blank. Slew rate. Now this is interesting. Slew rate is the rate at which output voltage changes with respect to input voltage. So ideally we expect these square waves, rectangular waves. It does not happen like this because there is always an RC lag. So what happens is that it rises like this, again falls like this. So the slope of this rise or fall is what we call slew rate. Ideally this is vertical, hence the slew rate is infinity, because in 0 times the voltage will rise to, let's say, 0 to plus 15 volts. So slew rate will be plus 15 minus 0 divided by 0 seconds. So it will be infinity. However, in real life this is not the case. So it will be some volts over microseconds. A good op-amp will have an order of this, 2 volts per microsecond, 10 volts, something like that. CMRR, as I told you in previous slide, this AC, so AC upon AD, 20 log AC upon AD is your CMRR. So as I told you, an ideal op-amp will have AD greater than AC. So this value will be very high. Sorry, AD upon AC. Depends on how you want to see it. Some expresses AC upon AD also. So when this value is very high, this means AC is negligible. This is a log term. So let's say it's 10 to the power 4 times higher. Let's say AD is 10 to the power 4 times AC. Now if I put this here, so it will be 20 log 10 to the power 4, which comes out to be 80 dB. So this is a good amplifier where CMRR is very low. So AD is greater than AC, 10 to the power 4 times to be in this example. So as I was telling you, usually for good op-amps this is in the range of 60 to 100 decibels. Now this table is just for, you don't have to remember these values. It's just that when you solve a numerical, so you must have an idea that your ideal values are something like this. If input impedance you are getting 10 ohms, this means you have made a mistake. If output impedance you are getting 2 kilo ohms, you have made a mistake. If offset voltage is a few volts, you have made a mistake. So that's why it's good to have just an idea in back of your mind, right? And this is what I was telling you. So let me just, okay, so V out, this is the formula that you need to take away from this. V out is equal to A open loop times V plus minus V minus. All the questions we'll solve using just this. That's it. No other formula. This is the only formula that you have to remember. This is OL stands for open loop. We'll see what does open loop even mean. We'll see that in a minute. Right. So let's talk a bit about, let's solve a question, not a question but a problem. What is a comparator circuit? Comparator circuit compares two values. Which value it compares? It compares the value between the voltage applied at positive terminal and negative terminal. So I have applied a Vref at negative terminal. So let's say for the sake of discussion that Vref is 2 volts for this example, and let's say I am applying a Vin. So let's say Vin starts from let's say minus 10 volts to 10 volts. So what should happen? This circuit will simply say this: if Vin is less than Vref, then output should be AOL times V plus minus V minus. So let's solve this. Let's say for minus 10 volts it will be AOL times minus 10 minus Vref is 2 volts. So it will be minus 12 times AOL. And remember, AOL is 10 to the 5. So the answer is minus 12,000. But remember, we cannot go beyond VCC. So when Vin is less than reference voltage 2 volts, when Vin is less than reference voltage, I'll change the color of my pen for more clarity. So when Vin is less than V reference, we will get output as minus VCC. When V in is greater than V reference, so this value will become simply positive, and we cannot go beyond VCC, so we'll get this value. So what it's doing, it's comparing. Just look at this. If V in is less than Vref, your answer is negative. If V in is greater than Vref, your answer is positive. So it's a comparison circuit. That's why it's called a comparator. This is the most basic circuit then you will see, and this is the summary of this circuit. Now let's now take an example. Vref equal to 2 volts and V plus equal to 2.001 volts. Can somebody tell me what will be the answer? Vref is 2 volts, V plus is 2.001 volts. What will be the answer? Anyone? Hello, am I audible? Am I audible?
Yes, sir. Yes, sir.
Okay, fine, I'll solve it. So output voltage would be V out equal to simply AOL times V plus minus V minus. AOL is 10 to the power 5. V plus is 2.001 volts minus V minus is 2 volts. So we'll get 10 to the power 5 into 0.001, which is 100 volts, which we cannot get, so it will saturate at plus 15 volts or plus VCC. Let's say plus VCC is 15 volts. Now this is a very bad comparator. This means, as this is noise, 0.00 volts is noise, so just due to the noise it will saturate very suddenly. So this comparator is not a very good circuit. For comparing large values it's good, but it cannot tolerate noise. Hence we need feedback. Negative feedback will provide a stable output. It will not always saturate. We'll see, we'll solve problems. It will not behave this, let's say input voltage just increased by 0.00 due to some noise, it's saturated. No, it will not happen like this. Negative feedback will ensure that. Positive feedback, negative feedback gives stable output, and some examples which we will solve are integrator and differentiator. Positive feedback, why we call it negative feedback? Because output, this is V out, is connected to the inverting terminal. So some output, some V out voltage is being reflected at this node, hence you call it negative feedback. If some component of output voltage is getting fed to non-inverting amplifier, we call it positive feedback. If you load the plus node, this also usually gives unstable output, but these are still useful. These are used in oscillators, and one of the famous oscillators is Schmitt trigger. Right, now as I told you, negative, usually most of our circuits and your problems will be to negative feedback, because this is a stable circuit. It's trustworthy, so we can expect this will not go bad just due to some noise or some manufacturing defects. No, it will not happen like this. This is a stable circuit. Hence the operational amplifier is more often than not used in negative feedback mode. There are four kinds of negative feedback. So this is called series shunt. Why is this called series shunt? Because we take somebody is unmute. Can you please mute yourself? There is some noise coming. Thank you. So is this called series shunt? Why it's called series shunt? 1 second. It's called series shunt because we take from the output side, we take this as shunt value. So output is taken as a shunt, it's fed to this feedback network, and while putting in the input we are giving it a series. You see that this is a series circuit and this is a parallel circuit, hence shunt, and this is series. There are four configurations. Second is series shunt. What do we mean? We simply take the current, you can see this is in series, right, and we provide the input. While providing feedback, we provide in parallel. Hence, this input side is shunt, output side is series. We call it shunt series. Similarly, if we take output feedback, if we take output as shunt and we provide input also as shunt, this is called shunt. If we provide output as series and we provide input as series, this is called series. These are four configurations which you will see, and we'll see in our problems. Usually in operational amplifier, we'll be using this one. This is the most commonly used for negative feedback as far as operational amplifier is concerned. but please remember that others are also possible. This is the most famous one and most commonly used. Excuse me. Right. So why do we even need negative feedback? I told you, small voltage difference. I just calculated. If there is some noise and voltage 2.001, it will immediately saturate. Negative feedback can protect us in some, so there will be no immediate saturation. So this will not happen for negative feedback circuits. Tunable. Now the gain is always fixed, 10 to the power 5. However, by providing feedback, we can change this gain. So who decides the gain? I told you. So 1 second, where is that? So gain, I said 10 to the power 5, open loop gain. But by providing feedback circuit, we can change this. We can make it 10, we can make it 100, we can make it 10 to the power 4. We cannot increase obviously beyond this, but we can change it. So it's tunable. Manufacturer gives it 10 to the power 5, but just by putting some resistors, like you put a resistor here, you can change the gain. We'll see. We'll do that. So that's the best, that's the most precious advantage of negative feedback, that the gain is tunable. The gain is tunable, and it depends primarily on external resistance, which we can put in the circuit. So I can put 10 kilo ohm, 1 kilo ohm, depending on what resistance I am putting in my feedback network. I can change the gain, I can tune the gain. And the third advantage, which we'll see in some later sessions, that negative feedback circuit provides better performance in terms of high bandwidth, low input impedance, low output impedance, and high input impedance. We saw that output impedance ideally should be 0, but that's not the case. We get few milliohms. Similarly, output impedance ideally should be infinity. That's not the case. We get a few mega ohms. We'll see in a future session that how negative feedbacks helps us achieve these values. Now, till now I have only talked about the theoretical aspect of operational amplifier. If you have any doubts, some clarifications, you can ask me now or later also, but it's better that you ask me now, so that if you have any doubts till now I've talked about, we'll be solving questions now onwards, the next part. Any doubts you guys have? Okay, I'll move forward and we'll solve the simplest problem that you can get with an operational amplifier. So whenever you're solving problems, you must identify a few things first. You must check whether the feedback network is there or not. First check, always, feedback network present or not. Second, if it is present, then is it positive or negative? And thirdly, if it is negative or positive, whatever, you must check the value of what resistances we are playing with. Okay. And fourth thing, it's a good practice to check in case of feedback networks, what's the configuration, series, shunt. So it's a good practice to do that. And a question has been asked just directly based on this, that what is the configuration of the op-amp in the given the circuit was given in the problem, and we were supposed to identify that what is the configuration, series shunt or shunt. So I'll solve this problem. So we have an operational amplifier. Okay, one more thing, assume that it's an ideal op-amp. Always assume unless the question says otherwise. What is an ideal op-amp? So R in is infinity, R out is 0. Always assume that. This means there is no input current, so current going here in this op-amp is 0, in this op-amp is 0, and flowing out of here is 0. Always assume this. This will really how should I put this, it will simplify your problems to a great extent. Always check whether the question says whether it's an ideal op-amp or not. Now we'll assume, since nothing is said, we'll assume it's an ideal op-amp. So no current flowing here, and no current flowing out of the op-amp. Right. Is the feedback present? No, feedback is not present. This is completely an open loop configuration. So open loop configuration circuits are nothing but comparators. Very simple. Okay. So now we need to compare. So what's the voltage? So V in must be compared with whatever value it's here. Okay. So I'll draw the circuit again. So it's showing, V in is showing, and we need to identify the correct output. So I'll draw the circuit in my next slide. Okay. So this is V out, this is V, so this is V in, and as we saw this is V negative, and there is a potential divider here with 4k. This is plus 5 volts, 4k and 1k, right? So before solving this we need to, and this is the saturation voltages, it's fine, we'll see that. So V in must be compared with so positive terminal must be compared with negative terminal, right? That's what a comparator circuit does. So what I'm going to do, V in must be compared with this value, but we don't know this value. So how do we calculate this value? We apply KVL in this loop. Remember, there's no current flowing here. Current is 0 here, 0 here and 0 here, right? So I can simply apply KVL here. So I'll write 5, let's assume the current is I here, 5 minus 4k times I minus 1k times I equal to 0. This means 5 minus 5k times I equal to 0. So I will come out to be 5 over 5k. This is 1 milliamps. Okay, so current is 1 milliamps, and I need to find this reference, the voltage here. So I can simply write V minus equal to 1 kilo ohms into 1 milliamperes, applying Ohm's law across this resistor. This will come out to be 1 volts. Very good. So now we know that reference voltage is 1 volts. What does this mean? This means simply whenever V in is greater than 1 volts, we will get plus V sat, and when V in is less than 1 volts, we'll get minus V sat. Very simple problem. So this is our V in. So I told when V in is greater than 1 volts, we should get V sat, and when V in is less than 1 volts, we should get minus V sat. Very good. So let's say in this option, when V in is greater than 1 volt, so V in is greater than 1 volts in this region, correct? So what we should get is V in is greater than 1 volt, so we should get plus V sat. So we are getting plus V sat, correct? We are getting this here. If V in is less than 1 volts, we should get minus V sat. So below this point we are getting minus V sat. So this is correct here and correct here. This seems like the correct answer, but I'll just, for the sake of completeness, I'll confirm. V in is greater than 1 volts, so this is V in greater than 1 volts. The value should be plus V sat, which is not. So this is wrong. This is wrong, obviously. Here V in, okay, we must compare with Vref, which is 1 volts. Vref equal to 1 volt. So greater than, if it's less than 1 volts, then it should be minus V sat, which is not the case here. This is also wrong. This is wrong, and similarly this is also wrong. So the option is A. Very simple comparator circuit. What we did was, this is the voltage divider that was given. We simply found out what is the reference voltage, and as soon as we found out the reference voltage, we wrote this expression. If V in is greater than V reference, we get plus V sat. If V in is less than V reference, we get minus V sat. Very simple comparator circuit. Just KVL in this loop. Why KVL? Because input currents were 0 and output currents were also 0, right? Second question. In the following circuit, what is the magnitude of V out if V in is equal to 1.5 volts? Again, I'll do simple those checks. If nothing is given, assume it's an ideal op-amp. Okay, what does an ideal op-amp mean? Means current here is 0, current here is 0, current here going out is 0. This is a good practice. Once you get enough practice, you'll assume it's 0. Right. Next, is there feedback? Is there feedback in this question? Please respond.
Yes, negative.
Negative feedback. Why? Because V output is being fed to negative, the inverting terminal of this operational amplifier, right? So what will you do? As I told you, since, okay, a very good trick here. We told this is infinity. What this means is that, so let's apply KVL, let's apply Ohm's law across this resistor. Okay, so I'm calling it as Rn. So I'll write V plus minus V minus equal to Rn times I in. Ohm's law across this resistor. So V plus minus V minus, Rn is, let's say, mega ohms, and I in is 0 because it's an ideal amplifier. So I get V plus minus V minus equal to 0. V plus equal to V minus. This is the most astonishing property of an operational amplifier. You can assume that whatever voltage is here, it's here. It is called a virtual short. I repeat, since V plus equal to V minus in an ideal op-amp, whatever voltage is on the inverting terminal, we can assume it to be on the non-inverting terminal, and we will see we can solve the problems very fast. So I'll write this question again on my next slide. It was a negative feedback circuit and this was 0. This is V out, this is V in, this is R, and I think this was 100 R if I'm not wrong. Yeah, 100 R, and the saturation voltage is plus 15 and minus 15, right? So what we just talked about is that whatever in an ideal op-amp, whatever voltage you see on this terminal can simply be, since this is virtual short, I can assume this to be grounded. The voltage is 0 here, so I'll assume this to be grounded. Now I'll simply apply. So now let me change the color of my pen. Right, let's assume a current I is flowing here. So no current is flowing here, no current is flowing here, and no current is flowing out here. So whatever current I is coming through, it cannot go here, so it has to come here, I, and then since I plus 0, KCL, applying KCL at this node, so I plus 0 will be I. Very good. So now what I can write, now what I'll write is, I'll write Ohm's law across this resistor. So what is Ohm's law? V in minus 0 equal to I times R. Again, Ohm's law across this resistor. I'll write 0 minus V out equal to I times 100 R. So IR equal to V in, and I get V out equal to minus 100 times IR. IR value is V in, so I'm simply replacing it here. So V out equal to minus 100 times V in, or I can write V out upon V in equal to minus 100. Now this is what I called gain, and to be more precise, closed loop gain. Remember, this would have some very high gain, 10 to the power 5, let's say open loop. But what determines closed loop gain? Simply the value of these resistors. The ratio of these resistors is the gain. So if this were, let's say 1000 R, our gain would have been 1000. That's what I told you. This circuit is very, very robust, and you can simply tune the gain based on the external resistances. So we got gain equal to minus 100. Very good. Now we were given V in as 1.5 volts, and we were supposed to find out V out. So V in is 1.5 volts, and we are asked what is V out. So we'll simply write V in here. So this implies V out equal to minus 100 times 1.5, which comes out to be minus 150 volts. Correct? Now, is minus 150 volts possible? No, it's not possible, because it will saturate at plus 15 volts or minus 15 volts. So this is not the answer. Remember, we got, although from the gain we got that answer should be minus 150, but no, the op-amp will saturate before that because Vsat is lower. So the answer here would be 15 volts, because we cannot go above 15 volts. If this value were 150, then yes, our answer would have been 150, but in this case it's not. Right. So this is a very simple feedback circuit. In this we talked about that how closed loop gain is determined completely by the external resistances. And one more concept we talked about, that you cannot exceed the saturation, whatever the saturation voltages are. Now again, this is the next question from GATE 2017. Very simple question. Again, we'll write only KCL and KVL, but first I will say, okay, the question says ideal op-amp. Very good. So ideal op-amp means this current is 0, this current is 0, and whatever voltage is here, I can assume the voltage same to be here due to the virtual short that I explained in the previous question. Right. So value of resistances is given, and value of V is given. That is given to be 10 millivolts, and we are required to find out current passing through R2 is, okay, current passing through R2. Let's assume, okay, so current going out here would be 0 again. So 0 current is flowing here, remember that, because this is 0. Okay, let's assume a current IL is flowing here, and let's say assume a current I2 is flowing here and I1 is flowing here. So I'll write KCL at this node. So incoming current is I1, outgoing there are two currents, 0 and I2, 0 plus I2, so I1 will be I2. Very good. So I'll replace this as I2. Okay, let's apply now, let's apply KCL on this node. Okay, so incoming current should be equal to outgoing current. So incoming current is 0, 0 equal to outgoing current is I1 plus IL. Okay, so I get IL equal to minus I1, and this is again equal to minus I2. So negative signs means I have assumed the sign is wrong, direction is will be, so the current is actually not flowing in this direction but in this direction, right? So now, yeah, we are almost done. So we'll simply write, now we need to try and find the value of this V out. If we find the value of we find the value of V out, we'll simply solve the problem. Now how do we find the value of V out? Right, so this is V, so this is 10 millivolts. I'm writing it as V in. This is also V in because of the virtual short, so this will also be V in. Simple, right? So now let's apply yeah, so let's apply Ohm's law across this resistor. So we will get V out equal to RL times IL. Okay, RL times IL. So RL we know is 100k and IL is I2, nothing but I2. So V out is 100 times I2, right? Now let's apply Ohm's law across this resistor now. So what we'll get is R2 times I2 should be equal to V in, right? And apply Ohm's law across this resistor. So I'll get V out minus V in equal to R1. I'll write all these Ohm's law expressions on the next slide because there's lesser space. So what we got was V out was 100 times I2, and second expression was V out minus V in equal to I2 times R1. Third expression was V in equal to I2 times R2. Now we know the value of V in, and I2 we need to calculate. So what I'll simply do is I'll put V in as here. Okay, all right, so let's try to do that. V out is equal to 100 I2, excuse me. Right, so R2 is V in, we were given, what was the value of 10 millivolts, divided by the value of R2 is 1 kilo ohms. So we'll simply get 10 microamps. So we'll put simply this value as 10 microamps. This is very simple. Actually at this when I solved this problem for the first time, I did it orally. You can also do it with practice. So the thing is, again, the concept is very similar. No current is flowing here, no current is flowing here, no current is flowing here out of the amplifier, and due to the virtual short, so whatever voltage you are applying here will come here directly, and because this is a wire, the same voltage will come here, and we can simply find V in by R2 is I2. Simple question, very simple problem. Next, again, this is a very similar problem that we did in the comparator circuit was there. So again, for the opamp circuit, again, since nothing is given, I'll assume it's an ideal opamp. Right, second thing, I check whether there is feedback or not. Yes, there is a feedback, and that feedback is positive feedback. Okay, So remember, I told you positive feedback are oscillators, right? So if I know this information, in this case I know, so this cannot be the answer and this cannot be the answer. Why? Because these are not oscillating. I know whenever there is a positive feedback, there has to be oscillation. As simple as that. So these two options are eliminated. So it's a 50-50. So now the only option is A or C. And we'll solve this, but I am just telling you. Oscillators in op-amps are like this. Not again, not like this, but it will have some slew rate. So it will be like this, like some triangular wedge, not like this. So I know the answer is this, but we'll determine that. So again, let's start. Since it's an ideal, so we'll assume this current is 0, this current is 0, and there's no current that's flowing out of here, right? So what will we do now? We'll try to find out the expressions. Okay, so let's do it. Okay, so this is the V out terminal that we have here. So again, since this is a virtual short, so value here would be V in. So I'll simply write applying Ohm's law across this 20 kilo ohms resistor, V out minus V in equal to, let's assume current here is I, and same current, since no current can go here, same current will have to flow here. So V out minus V in equal to 20k times I. Now apply Ohm's law across this resistor, V in equal to 2.2k times I. So I place the value of I from here to here. I get V out minus V in equal to 20k times V in over 2.2k. This gets cancelled out, so V out will be V in 1 plus 20 upon 2.2. Remember, these are in phase, so if V in is positive, V out will be positive. That because the input is being because we have a positive feedback. That's why. Oh wait, did I something wrong? Did I do something wrong? So V out minus V in is 20k times I, and V in, yeah. So this will turn out to be, this will approximately be around, so this is 9 plus 1 10. This is approximately 10 V in. Okay, so whatever the input is, the output will be 10 times. Okay, so our input is 1.5 times sine omega t. So our output will be 10 times 1.5 sine omega t. The frequency is not of a concern here. So what will this come out to be? This will come out to be again 15 sine omega t, correct? 20k by 10k, yeah, 15 sine omega t, right? So, and we know the saturation voltage is plus minus 10 volts. Very good. So we simply know that we cannot go beyond 10 volts, right? And this is actually in the problem, they should have provided a time scale, so that, but you can say that this will saturate very fast, because at, so let's say 10 equal to 15 sine omega t, depending on the omega, so that will be, so you can see that the sine wave will be clipped, this will not be complete. So above 10 volts you will not get nothing. So the closest option that I have here is this. I know this is not entirely correct, but these two cannot be, and sine wave has to be clipped. So assuming that frequency is high enough, so this can be the answer. So these are the only two options that we have to play with, and sine wave has to be clipped. This is the only way, this is the only option in which I can see some clipping. This is slightly misleading, but I would go with this option. Again, I'll summarize this. This is a positive feedback circuit, and we solved it again using, we found out the gain simply using the expressions for KVL or Ohm's law. That's it, right? So again, last question for today. So what we have is that circuit is given, nothing is given, assume ideal op-amp. Ideal op-amp means current here is 0, current here is 0, and current coming out of this op-amp is also 0. Very good. And virtual short, so if voltage Vi is here, so voltage Vi will also be here. Very good. Now the feedback configuration. Okay, so they are asking what is the feedback configuration. Now we know it's a negative feedback. but this is not what they're asking is the series shunt, series shunt, or shunt. We'll determine, but first let's calculate the gain. How do we calculate the gain? Very simple. Apply Ohm's law across this resistor. V0 minus Vi. Assume current here to be flowing I, and since no current can flow here, so all the current coming through this branch has to go through this branch. So V0 minus Vi would be 9k times I. Now apply Ohm's law across this resistor. It will be Vi equal to 1k times I. So I'll replace I as Vi over 1k. This is equal to, we'll replace this here, so we'll get V0 minus Vi equal to 9k times Vi upon 1k. K and k gets cancelled, so we get V0 equal to 10 times Vi. Okay, so V0 upon Vi is 10, and this is our gain. This is our gain that we are getting. Okay, right. So this option is eliminated, so because our gain is 10, this is the incorrect option. So now we have these three options left. Now we need to identify which configuration is this. So what we are taking is, we are taking the voltage, so that's so output size is what we have is a shunt, because we are taking the voltage, this is in parallel to this, so this is a shunt here. On the other hand, we are feeding in series, because the current is being, in this case it's 0, but we are feeding whatever current we are getting, we are feeding here, nothing is going in this case. So this configuration is what is called a series shunt configuration, and hence option C is the answer. In your op-amp circuits, more often, in fact, I have never seen a circuit which is not series shunt in op-amps. In gate questions which I am talking about, or net or just level, whatever, always you will, either it will be an open loop circuit, or if it's a feedback circuit, you will more often than not see that it's a series shunt. This is what you will always see, right? So this is all for today, but there are few shortcuts which we can learn. Remember, what was the gain here that we got? The gain here that we got was, closed loop gain we got was, where was it? Yeah, 100. So in these types of circuit, this is a trick that you can learn. The closed loop gain is, this is usually written as RF, and this is usually written as R1, you can say. So closed loops gain is simply RF over R1. We derived it. So this is a shortcut which you can try to remember, that in these kinds of circuit, this is the closed loop gain. Similarly, for these kinds of circuits, we calculated that the gain was this. So there's a shortcut for this again. So the gain would be, this is RF, and again this is R1. So it will be, gain would be RF plus R1 over R1. That's what we got, right? We got, yeah, this is correct. So this is what we got. So again, you can try to remember this. These are shortcuts, but even if I never remembered these formulae, because this is very simple Ohm's law. There's nothing, because depending on the types of circuits you have, you will get different types of formulae, and it becomes very, like, you get 10 circuits and you get 10 formulae. So I find it easier to derive it, because there's nothing, it's just Ohm's law across these resistors. Okay, so that's all from me. Now if you have any doubts, please go ahead, whether in the concepts that we discussed earlier or in the questions that I had solved. You want me to repeat any question, you want me to repeat a concept, please ask. Or if you have some doubts of your own, that's also welcome.
Sir, explain about the virtual shunt, virtual sort.
Virtual short, okay, I'll do that. Right. V out, V plus, V minus, right. Remember that there is a resistor sitting inside. We are assuming non-ideal for now, and then we'll derive why ideally it's a short, right? Let's assume a current I is flowing here, so whatever current is flowing in, which will simply come out, because there is no other node here, right? So what I'll do, I'll simply write Ohm's law across this resistor. Ohm's law says V equal to IR. Okay, so voltage across this resistor, it is V plus minus V minus. This node is V plus, this node is V minus, equal to current flowing is I, R is Rn. Okay, so I would be V plus minus V minus upon Rn. Very good. Now this is a real resistor, this is a real life scenario. In ideal scenario, I told you Rn tends to infinity, so let's put infinity here for ideal. This is a real op-amp. This is real op-amp. For ideal Rn, put limit Rn tends to infinity, and you will get V plus minus V minus over infinity. This will come out to be 0. Okay, so this current is 0. This current is 0, which makes sense. Rn equal to infinity means open circuit, so no current can flow here, right? Now let's look at this expression now. V plus minus V minus. Since there is no current flowing through here, okay, what we do is that we simply assume that it's a short. The current is so low that there will be virtually no voltage drop if we apply a KVL in this circuit. Even if Rn, let's say, now come back to the real life scenario, let's see Rn is some mega ohms. Okay, current here, because we are assuming an ideal case, current would be 0. Okay, so I would again come out to be, sorry, V plus minus V minus will come out to be I times Rn. Since we are assuming an ideal case, I is the product of these two terms is very, very low. It should be ideally like microamps or even nanoamps. So we ignore this and we simply say V plus is approximately equal to V minus. And this is what is meant by when we say virtual short. These two terminals are not shorted, but due to this configuration, they can assume to be shorted. That's what I meant to say. This is called virtual short. So whatever voltage is being reflected here, you can simply reflect it here. And note that this is not the comparator circuit. We're not talking about comparator circuits here. In comparator circuits, we even compare these two values. That's a different case. But if some feedback you have for solving those problems, let's say you have some negative feedback here, RF and some resistor R1 here, then you can assume that whatever voltage is here, due to the virtual short, that voltage is being reflected here due to this is due to Ohm's law across this resistor. That's what I meant by virtual short. Is it clear now?
Yes.
Okay, good. All right. Any other doubts that you people have?
Sir, series and shunt resistance.
Yeah.
If you can tell more about it, sir, because it is not quite clear.
Okay, I'll do that. I'll explain those terms again. Okay. I'll take just one example. This is the most common. This is the configuration that we find in our op-amp. So we'll talk about only this for now, right? So what you can see, so what you see here is that this is the reference. So let's assume this is ground, okay, and this is some output V out. This is our op-amp. Assume this is our op-amp. This is our V out, and the other is, there will be some reference in every circuit. There is some reference. Assume we usually don't show reference when we draw op-amp, but there is some reference which is grounded. Okay, it's assumed to be grounded. Now, but this is not V out, this is V out. So what I'll do is that whatever voltage that I'm getting, so this is the voltage that I'm getting, V out on this node, 0 on this node. Whatever voltages I am getting, I'm directly providing those voltages to my feedback network. Note that. So this is the reference voltage for feedback. I am providing ground here, and this is the input voltage to feedback network which I am providing V out. So what I am doing is that whatever voltage is being provided here is being provided here. This is like a parallel circuit. I'll draw a circuit here. So let's say this is 10 volts. this is 1 kilo ohms. Can you tell me what is the voltage applied across 1 kilo ohms resistor? This 1 kilo ohms resistor.
10 volt.
10 volts. Okay. What is the voltage applied across this 10 kilo ohms resistor?
Same 10 volt.
10 volt. So what I did is that whatever voltage is here, so let's say this is reference. So whatever reference, and let's call this node V out. Okay, just like this, and assume that this is the feedback network. In place of 10k, assume this is feedback. That's what I'm doing, right? Am I not doing that? I am providing V out, I'm feeding it to the input of feedback, and I am, whatever the reference of feedback is, I am giving it as a reference of the circuit. This is what I am doing. This is in parallel. You just told me 10k is in parallel, right? This is what is called, in technical terms, this is called shunt. This configuration is called shunt. When we provide the voltages in this way, this is called shunt. Hence this configuration on right hand side is shunt, and this is the output side. So output side we call shunt. Similarly, if we see, look at this example. So here it is V out. Assume this to be the reference. See, reference is being fed to reference and signal is being fed to signal without any resistors. So this is again in parallel. Again this is shunt. You see, reference is being fed to reference and signal is being fed to signal without any change in values. So it's short. Hence this is shunt. So this is what we mean by shunt. In series, what we do is that we provide whatever the output is through usually a circuit of, if not voltage source, but a resistor or something, which we see here. So every series thing, okay, again we'll solve it using a problem. 10 volts. What is the voltage? What is the voltage? Sorry. How should I say this? Yeah. What is the current flowing through 1 kilo ohms resistor?
10 by 1k. 10 volt by 1k. 10 milliampere.
10 milliamp. Right. Let's say I assume one more circuit here. Okay. Let's assume its value is 9k. Can you tell me what is the current now? It will be 1 milliamps.
1 milliamp.
But what's happening here? Just please understand. Whatever the signal, so this was reference earlier. This was the reference here. I am putting reference of first circuit to input voltage of second circuit. I'll draw it again. So this was my first circuit, remember that. This is my second circuit. What I am doing is that the reference, this is the reference voltage, this was the reference voltage for first circuit. So whatever the reference voltage first circuit is, I am directly putting into the input of second circuit. And similarly, whatever the reference voltage for second circuits, in this case second circuit is nothing but a resistor, is being fed to the signal of first circuit. This is what we typically call series. This is the series actually. So here you see that the reference circuit is being fed to the actual circuit. The value of voltages are not being directly provided. Hence this is called a series, because the current, any current if any, has to flow through this circuit. This cannot be directly fed to the amplifier. Here voltage in shunt, whatever voltage we get, we directly feed to the amplifier. In series, whatever current we get, we have to pass it through the circuit in order to feed it to the amplifier. So shunt is basically like bypassing in parallel shunt. If you are series, then the current has to be bypassed through the circuit. So whatever current is being drawn out of here, it has to go through like this. Otherwise it's not a complete path. This is not the case here. So whatever current you have, you can directly feed here. This is the reference. That's why it's called series shunt. Series, first term stands for the input side, which is series, because the feedback network is providing the current in series. However, the output is shunt, because whatever the output voltage, we are directly feeding to the feedback network. That's what it's meant by series and shunt. Better now?
Yes, sir.
Okay, good. Yeah, so that's it from me today. If you people have any doubts, please go ahead. Okay, if no, then we'll meet next week again. Tomorrow, next week again, it will be operational amplifiers, but we'll solve some more problems, and this time we'll have capacitors. So if you find time, read up on integrator differentiator circuits and what is the role of capacitor in an operational amplifier. Again, I'll be using simply KVL expressions and Ohm's law to solve the problems. So yeah, that's it. Thank you. Bye bye.
Thank you, sir.
Yeah, bye.
Bye.